I'm going to talk about how we can use the maximum likelihood to derive the sum of squares error. Recall that the maximum likelihood is interpreted this way. Say you are given some distribution p of x, and say you're given a dataset where your dataset is a set of data points up to n data points. And if you plot these n data points here, say this is x1, x2, x3, x4, for example, the likelihood of observing your data, let's call it P of observing your data given some parameter W, is equal to the P of x times P of x2 dot P of xn. And note that this parameter W governs the shape of the distribution here. We can summarize this to be the product of P of xn given W for n is equal to 1 up to d, which is the number of data points. Then the second part is the sum of squares error. Recall that this is used to fit a regression model to your data, such that if you're given, say, y that takes in x and has the parameters w, you want to fit this y such that it closely resembles the true values of y. And one way to do that is to minimize the sum of squares error is equal to the sum of the difference of your prediction and the true value of y xw minus y true squared, and you sum that up from the first value, so that's from n equals 1 to n, and so this is y of xn minus y of n. Let's call this the true value. Now we want to show the relationship between maximizing the likelihood and the sum of squares error. To do this, we're going to consider a model y given x and some parameters w, but we're going to add Gaussian noise epsilon, such that epsilon is taken from a normal distribution with mean 0 and with variance sigma squared, and we're going to call this t. Note that this function is deterministic, but this adds randomness, and we can summarize this to be a probability function of getting t given your parameters and your input. And so that means given your input x, given your parameters w, and your sigma squared. And it turns out that this is equal to the normal distribution of t conditioned on your mean and sigma squared, where in this case, your mean is now defined as y of x given your parameter w, and your sigma squared is sigma squared. So one interpretation of this one is, say you're given your x here and your y there, and you're given this function y xw. Now when you add Gaussian noise, then you expect a distribution of possible values around your y x of w, such that this distribution is normal, centered around y xw, so it's the mean, with variance of sigma squared. This formulation here is valid. So for simplicity, let's just call this y, such that your probability of getting t given your parameters and input x w sigma squared is equal to the normal distribution of your t conditioned on y, which is a function of your w and x, and sigma squared. Now the next part is calculate the likelihood of this probability. Say that we have a dataset capital T of targets, or what you want to predict. So it's t1, t2, n, and you have n data points. So we want to calculate what's the probability of getting this dataset given your input and your parameters w sigma squared. And in this case, x is now x1, x2, xn. And recall that we initially called this capital D, but let's call it capital X. And from what we have defined here, the likelihood is now equal to the products of these probabilities. So that becomes the product of the normal distribution of t given y and sigma squared from n is equal to 1 to capital N. The next thing that we want to do is to maximize this. But it turns out it's easier to maximize the logarithm of this value. So you want to do max of the likelihood, but it's easier to evaluate the logarithm of the likelihood, and at the same time, maximizing the likelihood is the same as maximizing the log likelihood. So let us maximize the log likelihood instead. Let us get the logarithm of p, which is from here and that becomes summation from n is equal to 1 to big N of your normal distribution of t given your model y and sigma squared. Recall that the formula for your normal distribution given x, mu, and sigma squared is equal to 1 over 2 pi sigma squared to the 1/2 e to the negative 1 over 2 sigma squared times x minus mu squared. And getting the ln or logarithm of this gets us of 2 pi sigma squared to the negative 1/2. So I just place this to the numerator plus ln of e to the negative 1 over 2 sigma squared x minus mu squared. So this becomes equal to negative 1/2 times ln of 2 pi sigma squared plus this term simply becomes negative 1 over 2 sigma squared times x minus mu squared. Now going back to our formula here, it follows that this becomes equal to the sum of negative 1/2 n 2 pi sigma squared plus sum of negative 1 over 2 sigma squared times x minus mu. And in our case, mu is y. So this becomes x minus y squared. And we can simplify this further to be equal to negative capital N over 2 ln of 2 pi sigma squared minus n over 2 sigma squared times the summation squared. And remember, this is from n is equal to 1 to capital N. Same with this and that. And remember that this is the log likelihood, which is ln of p of getting your target data given x, w, and sigma squared. This numerator should just be 1 because we place the summation here. Now, we want to maximize the log likelihood with respect to the parameters of your model, w. So recall your model is y, x, w, and we need to figure out what's your w to maximize the likelihood. Now, because we are more concerned with maximizing the likelihood with respect to w, we only need to look at the terms that has w in it. From the perspective of maximizing the log likelihood with respect to w, this is a constant. So we don't need to think about that with respect to w. The only term that will be affected is this term because y is a function of w. So it's y x w. The sum of n equals 1 to n of x minus y x w squared is the sum of squares error. Notice the negative sign here, which means that maximizing the log likelihood implies minimizing the sum of squares error. In summary, we have shown that maximizing the log likelihood of a model y of xw with respect to its parameters such that y has an additional error term that's taken from a normal distribution with variance sigma squared is equivalent to minimizing the sum of squares error of the prediction of the model and the true value squared.